Pharmaceutical technology outlines solubility, dissolution mechanisms, and factors affecting the rate of dissolution. Solubility. You know that the attractive forces between atoms lead to the formation of molecules and ions. Also, the intermolecular forces, which are developed between like molecules, are responsible for the physical state of the matter, whether it's solid, liquid, or gas, under given conditions such as temperature and pressure. When a solute dissolves, the substance's intermolecular forces of attraction, whether dipole-dipole or van der Waals forces, ion dipole forces, and hydrogen bonding, must be overcome by forces of attraction between the solute and the solvent molecules. This entails breaking the solute-solute forces and the solvent-solvent forces to achieve the solute-solvent attraction, like the following diagram. This is the solvent-solvent attraction, solute-solute attraction. These force should be replaced by solvent-solute attraction. Although there are no exact rules for predicting the solubility of a chemical agent in a particular liquid، يعني لا يوجد هنالك قاعدة معينة لتحديد ذوبانية المادة في سائل معين، لكن هنالك أيضا توقعات من الممكن أن يعتمد عليها في تحديد درجة ذوبانية المادة في السائل. Experienced pharmaceutical chemists can estimate the general solubility of chemical compound based on its molecular structure and functional group. For example, the organic compound is more soluble in organic solvent like alcohol than in water. You know that there is a rule says that the like dissolve like. Therefore, if we introduce a polar group to this organic solvent, to the organic compound, then the solubility of this organic compound will increase in water, according to the like dissolve like. Also, salt of this organic compound will be more soluble in water than in case of the organic solvent. Also, if we introduce, for example, halogen group to the organic compound, the solubility will not increase like if we introduce a polar group, but it would be decrease. Why? Because in this case, we increase the molecular weight without increasing the polarity of the compound. Dissolution mechanisms. The dissolution of a crystalline solid in a liquid may be regarded as being composed of two consecutive stages, assuming that it's molecular in nature, And the same is applied for ionic drug. First is an interfacial reaction that results in the liberation of solute molecules from the solid phase to the liquid phase. It involves the replacement of crystal molecules by the solvent molecules, as represented in this figure. The crystal molecules are replaced by the solvent molecules. The solvent-solute forces of attraction must overcome the cohesive forces of attraction between the molecules of the solid. On leaving the solid surface, the drug molecule must become incorporated in liquid phase or holes, as you see in this figure. Assume that these are the solvent molecules. The solvent molecules should arrange together to form a cavity, and then the liberated solute molecules from the solid surface will be incorporated in this cavity that is called holes in order to form solution. The second stage is diffusion through the boundary layer. What is the boundary layer? Boundary layer is a static or slow-moving layers of liquid that surround all solid surfaces that are surrounded by liquid. As you see this diagram, this is the boundary layer. This is the boundary layer. It is a static layer surround the solid surface that is surrounded by the liquid. So, in this stage, the solute molecules must migrate through the boundary layers to the bulk of the solution. During diffusion, the concentration of the solution in the boundary layers changes from being saturated, CS, at the crystal surface to being equal to that of the bulk of the solution, C, at its outmost limit. This is the boundary layer, this is the crystal solid surface, and this is the solvent. Here, after the solute particle migrate from the solid surface, as I mentioned in the first stage, it migrated from the solid surface and then replaced by the solvent molecule. Then the solute molecules will diffuse throughout the boundary layer. In the boundary layer, the concentration of the solute is represented by CS, which is a saturated concentration. This concentration changes to C when the molecule of the solute diffuses from the boundary layer to the bulk of the solution. That means there is a continuous diffusion of the solute molecule from the boundary layer toward the bulk of the solvent, because C here is less than CS. Dissolution rates of solids in liquids. The rate determining or rate limiting step of dissolution, which is the slowest step, is the diffusion of dissolved solute through the static boundary layer of liquid that exists at solid-liquid interface, while the interfacial step is virtually instantaneous. يعني تكون المرحلة الأولى من الذوبانية التي تطلق عليها interfacial step تكون آنية. The rate of diffusion throughout the boundary layer will obey Fick's law of diffusion. Fick's law of diffusion states that the rate of change of concentration with time is directly proportional with the difference in concentration between the two sides of the boundary layer. That means the rate of change of concentration with time equal to K multiplied by delta C. dC on dt equal to rate of change of concentration with time. Delta C is C1 minus C2. At equilibrium, C1, which is the concentration of the solute in the boundary layer, will be equal to the saturated concentration, and C2, which is the concentration of solute in the bulk of the solution, will be equal to C. K is a proportionality constant. That means you should keep in your mind that diffusion of the molecules throughout the boundary layer follows the Fick's law of diffusion. That means as the difference in concentration of the solute molecule between the boundary layer and the bulk of the solution increase, the rate of change of concentration with time will increase also. An equation known as Noyes-Whitney equation has found a great usefulness in the estimation or prediction of the dissolution rate of pharmaceutical particles. يعني في أغلب الأحيان نعتمد على معادلة تسمى Noyes-Whitney equation في تحديد معدل الذوبانية للمادة. Noyes-Whitney equation states that the rate of mass transfer of solute molecules or ions through a static diffusion layer is directly proportional with the area available for molecule or ionic migration A and the concentration difference across the boundary layer, and it is inversely proportional with the thickness of the boundary layer. Delta C equal to CS minus C, which is at the equilibrium state when the concentration of the solute in the boundary layer will be equal to the saturated concentration. K is the diffusion coefficient and commonly given the symbol D. So we depend on this equation to determine factors that affect on rate of dissolution. In the present context, Delta C is the difference in concentration of the solution at the solid surface C1 and the bulk of solution C2. At equilibrium, the solution in contact with the solid, which is C1, will be saturated, as I said before, and equal to Cs. Thus, delta C, which is equal to C1 minus C2, then will be represented by saturated concentration Cs minus C. If C2 is less than saturated, which is the usual case, the molecules will move from the solid to the bulk as during dissolution. If the concentration of the bulk C2 is greater than this, the solution is referred to as supersaturated. In the first condition, when C2 is less than saturated, that means the solution will be subsaturated. It is not till now reaching the equilibrium state. So it is subsaturated. C2 is less than C1. But if C2 is greater than C1, then the solution is referred as supersaturated. In this case, the opposite will occur. That means the solid molecules will be in the direction of bulk solution to surface, as in case of crystallization. يعني عندما يكون تركيز السوليوت في المذيب أقل مما هو عليه في البوندري لاير، عند ذلك الذوبان سوف يستمر باتجاه السوليد سيرفيس إلى البلك of the solution، وهنا يكون المحلول لم يصل إلى مرحلة الإشباع، يكون subsaturated. لكن إذا كانت C2 التي هي تركيز السوليوت في السولفنت أكثر من C1، في هذه الحالة سوف يكون اتجاه حركة الجزيئات بالاتجاه المعاكس، يعني من البلك باتجاه السوليد سيرفيس، وهنا يحدث الكريستاليزيشن ويكون المحلول في هذه الحالة super saturated. If the volume of the solvent is large or solute is removed from the bulk of the dissolution medium by some process at faster rate than it passes into solution, then C remains close to zero, and the term Cs minus C in the equation may be approximated to Cs. The dissolution is said to occur under sink condition. يعني متى تحصل السينك كونديشن؟ سينك كونديشن تحصل عندما تكون قيمة C2 التي هي في حالة الإشباع يرمز لها C مقاربة إلى الصفر، يعني تكون قيمتها مهملة. متى تكون قيمة C مهملة؟ عندما يكون حجم السولفنت كبير، بحيث يكون تركيز المادة في داخل هذا السولفنت يكون تقريبا مهمل neglected. وكذلك في حالة إذا كان هنالك ميكانيكية معينة تؤدي إلى إزالة السوليوت باستمرار من bulk of the dissolution medium، بحيث تكون عملية الإزالة أسرع من مرور البارتيكل أو الموليكولز into the solution. في هذه الحالة تكون قيمة C مقاربة إلى الصفر، and Cs minus C will be represented by Cs only. This is sink condition. You should keep in mind that sink condition occur when the volume of the solvent is large and if the solute is removed from the bulk of the dissolution medium by some process. In this case, C equal to 0. In most condition, C will be equal to about 10% of the value of CS, and CS minus C in this case equal to CS because C will be neglected, as represented by the equation dm, rate of change of mass with time, equal to D, which is the diffusion coefficient, multiplied by S CS and divided by H. In this case, CS replace the delta C, which was CS minus C, because C is neglected under sink condition. This equation under sink condition, which is Noyes-Whitney equation, but value of C here is equal to 0. Sink condition occur or may arise in vivo when a drug is absorbed into the body from its solution in the gastrointestinal fluids at faster rate than it dissolves, as in case of tablet. That means the concentration of the drug in the body fluid or gastrointestinal fluid will remain very small, that may be neglected because the absorption process is faster than the dissolution of the drug from the dosage form, such as in case of tablet. In this case, C value will be neglected and sink condition will occur. That's why the patient should be advised to take glass of water with tablet in order to enhance the rate of dissolution. So sink condition will occur and the process will continue in the direction of movement of the solute particle from the solid surface toward the gastrointestinal fluid. Non-sink condition, which is the opposite one, arise if solute is allowed to accumulate in the dissolution medium. Here, the solute will accumulate. That means the C value will be large or high. When C builds up to such an extent that it equals CS, that means when CS and C are equal to each other, then delta C will equal to 0, and then the solution rate will be 0 also. That means the solution will be stopped. Factor affecting the rate of dissolution. Clearly, increases in those factors on the top of the right-hand side of the Noyes-Whitney equation will increase the rate of diffusion and therefore rate of dissolution, and increases in the factor at the bottom of the equation will result in a decreased rate of dissolution. The opposite is true. For example, starting with the surface area of undissolved solid. The surface area of the undissolved solid is affected by several factors like size of solid particles, dispersibility of powdered solid in the solution medium, and porosity of solid particles. Size of the solid particles. You know that the surface area is of the particle, of the isodiametric particle, is inversely proportional with the size of this particle. That means if we reduce the size of the solid particle, then the surface area will be increased or will be increased. This reduction of the size of the particles should be to certain limits because very fine powders may float on the surface of the solution and then the solubility will be reduced. Other factor that affect on surface area is the dispersibility of powder solid in the dissolution medium. If solid particles form coherent mass in the dissolution medium, then the surface area available for the solution is reduced. Therefore, we need to add wetting agent in order to improve dispersibility of the powder solid. Also, porosity of solid particles can affect on surface area of undissolved solid and then on the rate of dissolution. Because pores in some material, particularly the granular one, may be large enough to allow the access of the dissolution medium and outward diffusion of the solute molecules. This is low surface area, particles inside the solvent, and here is high surface area of the particles. The particles are cohered together here, and therefore these particles, when they are in a coherent mass, they result in small surface area that are exposed to the solvent medium, where when these particles dispersed in the solution medium by addition of, for example, wetting agent, then the surface area exposed to the solvent will be increased, and then the dissolution rate will be increased also. The other or the second factor that affect on the solution rate is the solubility of solid in the solution medium. Rate of dissolution increases proportionally with increasing difference between CS and C. Therefore, when CS is increased, then the rate of dissolution will be increased also. Therefore, we depend on factors that affect on saturated solubility in order to enhance the solubility of solid in the solution medium and later the dissolution rate. For example, temperature, nature of the solution medium, molecular structure of solute, and crystalline form of solid. presence of other compounds. We discuss these factors later in details. The other factor that affect on rate of dissolution is the concentration of solute in solution at time t, represented by C. Rate of dissolution increases proportionally with increasing difference between CS and C. Thus, low C value speeds up dissolution rate. C is affected by volume of dissolution medium. For example, if the volume of the solution medium is C, then C value can rapidly increase during dissolution and approach CS. If the volume is large, then C may be negligible. That means it is very small. That may approximate to 0. And then CS minus C will be equal to CS. This is sink condition. The second factor that affect on C value is any process that removes the dissolved solute from the dissolution medium. For example, adsorption onto an insoluble adsorbent, or partitioning into a second liquid that is immiscible with the dissolution medium. Also, removal of solute by dialysis or by continuous replacement of solution by a fresh dissolution medium can result in decrease in C and thus increase in the rate of dissolution. يعني كما ذكرنا السينك condition تحدث في حالة كون حجم المذيب كبير بحيث أن السي فاليو تكون قليلة، وكذلك في حالة إذا كان هنالك ميكانيكية معينة تؤدي إلى استمرار إزالة السوليوت المذاب داخل السولفنت، وبالتالي بقاء تركيز السوليوت داخل السولفنت في البلك قليل بحيث ممكن اعتباره مهمل. The other factor that affect on rate of dissolution is dissolution rate constant, K. It's affected by diffusion coefficient of solute in the dissolution medium. This diffusion coefficient is affected by, for example, the viscosity of the dissolution medium and molecular characteristics, for example, size and shape of the particles and so on. Thickness of the boundary layer is another factor that affects on rate of dissolution of the particles. Thickness of the particle, thickness of the boundary layer is affected, for example, by degree of agitation. As the degree of agitation will be increased, then thickness of the boundary layer will be decreased, and in this case, the rate of dissolution will increase. Also, this thickness can be affected by, for example, speed of stirring shape, size, and position of stirrer, and volume of the solution medium.